We're used to doing long division with real polynomials, so let's try it over Z mod 3. The problem is, apply the Euclidean algorithm to find the greatest common divisor of the polynomials f of x and g of x. These are going to be polynomials over Z mod 3. Once we've done that, we'll want prime factorizations. Then we'll want to find the coefficients for Bezout identity in this case. Now, for 1, we note we have Z mod 3 adjoin x. So Z mod 3 is a field, so this is a Euclidean domain. That means we can apply the Euclidean algorithm to find greatest common divisors. Now for that, we're going to repeatedly solve equations of this type. So we have f equal to g times q1 plus r1. We're solving for q1 and r1. We'll have r1 is equal to 0, or the degree of r1 is strictly less than the degree of g. To repeatedly solve this, to move to the next step, we're going to move all of our coefficients to the left by 1 and then solve again. So instead of f and g, we use g and r1. Now, we keep repeating. Eventually, we're going to have an equation where the new r that comes out is going to be equal to 0. And the greatest common divisor is going to be the previous r that we found. In our case, for our first step, we're going to have f under the division sign, g here. And then when I do the long division, the q is going to be the x plus 1, the quotient. The r is going to be the remainder. Now for long division using Z mod 3, the thing we note, procedure is going to be the same as always. So for long division, what we're doing, we're going to match, multiply, negate, add down the columns. Only trick here is when we negate, we have that minus 1 is equal to 2, minus 2 is equal to 1, and 2 times 2 is equal to 1. So for instance, in this first step, so we match, we're going to multiply by an x, we get this. When I negate, I can go down the columns here and here as usual because things match. Here we're going to have a minus 2. Minus 2 is equal to 1, so what will come out is an x to the 4th power. And then everything else is as usual. When we go to the next step, same idea. When we match, we'll have a 1, x to the 4th, x to the 4th. Then here I'll have that minus 2 again, comes down as an x cubed. So when I solve this, that gives our first equation. I have f, I have g, we have q, the quotient, and then we have r, the remainder. So we get this equation here for our first step in the Euclidean algorithm. For the next step, we shift everything to the left by 1. So now, we're going to put g of x under the division sign. Our divisor is now x cubed plus x plus 2. And then I just proceed as usual, as before. That gives our second equation for the Euclidean algorithm. We shift everything to the left by 1. So we have this long division here. We note the remainder is equal to 0. So this is going to be where we stop. Answer is, greatest common divisor is the last non-zero r that we computed. So x squared plus 2x plus 2. Of course, we want to check our work. So I want that x squared plus 2x plus 2 divides into f and g cleanly. And we'll find the prime factorizations to be sure that there are no other matching factors. Now, for the g of x, we could have done the problem differently. I could have factored out the x squared. We note the x squared is not going to divide into the f of x, so it would have been enough just to check if x squared plus 2x plus 2 divides into it, because this polynomial is irreducible. You'll note if we put 0, 1, or 2 into here, we're not going to get any zeros, so that'll mean no linear factors. So the only possibilities for factoring a quadratic, either it's an irreducible quadratic or it factors into 2 linear factors. This has to be irreducible. Now that gives a prime factorization of g of x. For f of x, we need the long division to get the other factor, so I leave that to you. Our other factor is x cubed plus x squared plus x plus 1. Now, it's a cubic, so 3 things can happen. Either it's an irreducible cubic, or it factors into a linear and an irreducible quadratic, or 3 linear factors. When we check, okay, against 0, 1, and 2, I get a 1, 1, and a 0. So 2 is going to be a root, which means x minus 2 or x plus 1 is going to be an irreducible factor here. Now, to take that out, I use synthetic division. So that's going to give me that the other factor is x squared plus 1. We check to see if this is irreducible. So when we put 0, 1, and 2 in, we get 1, 2, 2. So no zeros. So that's an irreducible polynomial. And we have our prime factorization for f of x. So we note greatest common divisor matches up, and then nothing matches if we consider the other factors. Next, recall Bezout identity. For the Euclidean domain, we can always solve for I and j in the equation if plus jg equal to greatest common divisor of f and g, where f and g are non-zero. The statement gives no indication of how to find I and j, but if we found the greatest common divisor using the Euclidean algorithm, all the work is done for us. We just need to back substitute. Now in our case, okay, what do we have here? Well, you'll note if we multiply the first equation by x plus 2, we'll be able to get rid of this term here by substituting out using equation 2. So when we work all this out, we get the equation. Okay, so I is going to be minus x plus 2, j is going to be x squared, and I'll leave it to you to work this out to check. One last thing. Recall, if we're working with a polynomial over a field, okay, we can always find another field that extends the original field such that our polynomial factors into linear factors. So the f of x that we're using has this factorization over z mod 3 with two irreducible factors in it that are quadratics. Now we want to break those down. So how do we do that? Well, the idea is going to be we take one of these irreducibles. That'll generate a maximal ideal in the polynomial ring. When I take the quotient, we're going to get a finite field that extends z mod 3. Now the way we should think of this is that we're just setting this maximal ideal. We're setting all of its elements equal to 0. So we're really just adjoining an element such that u squared plus 1 is 0, or u squared is equal to minus 1. So working over z mod 3, minus 1 is equal to 2. Now, to get a feel for this, okay, we've proved that group of units for a finite field forms a cyclic group. So if I take 1 plus u, that's going to generate group of units. So it's just going to sweep out all the non-zero elements in our field. So I'll leave it to you to check that. Now with that, we go to our other polynomial. I want to see if any of these elements give us zeros. So just by doing a little, okay, we just hunt. 2 plus 2u will give us 0 in this polynomial, as will 2 plus u. So I could factor this over our new field. So that means complete factorization of f of x is now given by x plus 1. X squared plus 1 is going to factor into x plus u times x plus 2u. And x squared plus 2x plus 2 is going to factor into x minus each of these, or x plus 1 plus u, x plus 1 plus 2u. Now I leave it to you to check by multiplying everything out.